Alright, this is our second review on advanced polynomials, preparing for a test on advanced polynomials. We're going to do it all. Let's dive right in. Problem number 1. Do these graphs represent even, odd, or neither functions? Remember, it'll be even if it has y-axis symmetry. In other words, if the y-axis splits it right down the middle as a mirror image on both sides, it'll be even symmetry. Like this one. This graph over here is even symmetry because it has y-axis symmetry. It's identical on both sides of the y-axis. On the other hand, it will be odd symmetry if it has origin symmetry, rotational symmetry around the origin. This graph right here is odd because it has rotational symmetry. If I rotate this graph upside down around the origin, it's going to look exactly the same as it did the other way. Well, you get the idea. Okay, so that's odd. It looks the same upside down, rotated around the origin. This one is neither, because this does have rotational symmetry, but the point around which this would rotate is over here someplace. This would be the center of rotation for this particular graph, not the origin, so that's neither. Okay, now if I want to determine algebraically whether or not the functions are even, odd, or neither, I have to do a little bit of work. They should be able to tell at a glance whether or not these functions are even, odd, or neither, but we're being asked to do more than just that. But let's go ahead and know the answer ahead of time. If all of the exponents are even, then it will be an even function. If all of the exponents are odd, then it'll be odd function. If we have a mixture of even and odd, then it's neither. So, for example, looking at number 2, I see this third power, and then this x is like x to the 1 power. All of the exponents are odd, so I know ahead of time this is an odd function. Now looking at this one, I see the 5, I see the 3. Now this constant is like having x to the 0 power. 0 is an even number, so I have two odds and an even, so that means I know this is going to be neither even nor odd. Now similarly down here I see the exponent of 4 and 2, and once again this constant is like having x to the 0 power. Again, 0 is even. So all even powers, so therefore I know this would be an even function. Now when they say algebraically, that's not what they mean though. Okay, so if you want to determine and prove algebraically that this is odd and neither and even, this is what I need you to do. First thing I need you to do is find the opposite of the function, which I will always show in red. The opposite of a function is negative f of x, and it's what you would get if you multiplied everything by -1. So this would become negative 2x to the 3rd power plus 4x. Okay, that is the opposite function. The next thing you need to do is substitute negative x for all the x's, and we will write that as f of negative x to show that we are about to plug in negative x everywhere. Alright, just put parentheses wherever you saw an x, and inside that parentheses put negative x. And we need to go on and see what we get. when we do that. Now, if you raise a negative to an odd power, the negative stays. So I have a positive times a negative is a negative. So I will have negative 2x to the third power. Nothing's happening to this negative. Negative times a negative is a positive. So this will be a positive 4x. Okay, so this is the result I get when I put in negative x. And this is the original function. And this is the opposite function. Okay? This function that we got, does it match either the original function or the opposite function? Alright, I'm hoping you can see that this matches the opposite function. And when the function you get by substituting negative x matches the opposite function, then it's odd. Okay? If it matches the opposite function, it's odd. If it matches the original function, it's even. If it matches neither, then it's neither. So we should write the following sentence. Since it matches the opposite function, it is odd. Okay. We'll do the same thing with the other two. So the first thing you do is you do the opposite of the function. So the opposite will be negative 7x to the fifth power minus 9x to the third power plus 1. Okay, so there is our opposite. Okay, here's our original function. And now let's put in f of negative x. So that'll be 7 negative x to the fifth power plus 9 times negative x to the third power minus 1. Now let's see what we get. Since it's an odd power, the negative stays. So positive times a negative is a negative. So negative 7 x to the fifth power. Again, odd power, the negative stays. Positive times a negative is a negative. So negative 9x to the third power. And then just bring down your minus 1. Okay, so our result from doing f of negative x is this. Does it match the opposite function? Well, it was looking that way at first, except for we have a negative 1 and they have a positive 1, so it doesn't match that. Does it match the original function? No, it does not match the original. So it matches neither, therefore it's neither, but we should write that down. Alright, since the result matches neither, the function is neither. Okay, meaning neither even nor odd. Okay, always wrap up with a little conclusion sentence. And last but not least, number 4. Once again, first we do the opposite of the function. So in this, multiplying everything by negative 1, we will get positive 3x to the fourth power minus 5x squared minus 7. So this is the opposite function. Okay, of course here is the original function. And now let's find f of negative x. Okay, so if we put in negative x, alright, 5 times negative x squared plus 7. Alright, if you raise a negative number to an even power, the negative goes away. So this is just going to be negative 3x to the 4th power. Poof, that negative goes away. Same thing here, another even power. Poof, that negative is going to go away. So I'll just have plus 5x squared. And that 7, just bring it down. Okay, so this is f of negative x. Alright, the result we get. So, does it match the opposite? No. Does it match the original function? Yes. Alright, you should draw an arrow to it and put a sentence. Okay. Since f of negative x matches the original function, the function is even. Okay. Alright, that is how you do that. And really, you know what, I'm going to go back. So here I said it. I should say since f of negative x matches the opposite. And here I said since the result. And I should have really said since f of negative x matches neither. The function is neither. Alright, it's all about what happens with f of negative x. Anyway, I've spent enough time on that. Okay, use long division to divide the following polynomials. Alright, so this is supposed to be divided by that, so what we have to do is we got to go 4x squared plus 10x plus 25, and that goes on the outside, you know what I mean? And then this goes on the inside, so I have 8x to the 3rd power. Now look at all these missing terms though. I'm going to need a couple of these placeholders. So I have the 3rd power, so I need plus 0x squared and plus 0x placeholders there. And then my minus 125. Now that's better. Okay, and the way we do this is we ask ourselves 4x squared times what will give me 8x to the 3rd power? Well, 4 times 2 will give me 8, and x squared times x will give me x to the 3rd power. So I'm thinking 2x. Once I have this 2x, I need to take it and I need to do the distributive property. Bam, bam, bam. So 2x times 4x squared, of course, is 8x to the 3rd power. Like we knew that. And let's see, 2x times 10x will be 20x squared. So plus 20x squared. And then 2x times 25 will be 50x. So plus 50x. Okay. Then we will subtract by changing the sign. So this will become minus, this will become minus, and this will become minus. So as I combine all these like terms, these cancel out. You know, 0 minus 20. So I have negative 20 x squared And I have negative 50x and negative 125. Alright, so once again I ask myself, 4x squared times what will give me negative 20x squared? Well, 4 times negative 5 will give me negative 20. And then I already have the x squared, so I don't need anything else. So 4x squared times negative 5 will give me negative 20x squared. Now I'll take my negative 5 and I will do the distributive property. Negative 5 times 4x squared, of course, is negative 20x squared. That's what we planned out. But negative 5 times 10x is negative 50x. Okay, and then negative 5 times 25 is negative 125. Okay, and then we will subtract by changing the sign. So this will become positive, positive, and positive. Well, look, in this particular case, everything cancels out. And so we get this 0 remainder. It divides in evenly. Alright, so as far as the answer is, this quotient is the 2x minus 5. Okay, and that's it. Just so you know, what if there had been a remainder? You know, something that other than 0. So that is the answer. I'm just doing a quick what if. Alright, so what if we had gotten a 10 down here or something? Then we would have gone like this. We would have gone plus 10 over, and it would have been over all of this. So it would have been over 4x squared plus 10x plus 25. That's what you do when you have a remainder. You stick it on, make a fraction out of it. But that did not happen. So this is the answer. Alright, number 6. Given this function, how many roots or zeros will the function have? Well, it's all about the degree. The degree is 4, so there should be 4 zeros if you count repeated zeros separately. Use the table below to find all roots of the function. Show your work. Let's see. Well, I see we have a 0 here, and we have another one here. Alright, so 3 and 6 are zeros. Okay, so let's go ahead and list those. So as far as zeros go, I have a 0 at 3, which by the way means I have a factor of x minus 3. And I have a 0 at 6, which means I have a factor of x minus 6. Okay, but there should be 4, so there should be 2 more. So I'm going to use my synthetic. So here I go. Starting with the 3, alright, and now I will need my coefficients. So I've got 1, negative 9, 22, negative 36, and 72. Alright, put a little box right here. Okay, 1 times 3 is 3. That's negative 6. Times 3 is negative 18. That makes 4 times 3 is 12. That makes negative 24 times 3 is negative 72. Now, I'm noticing that I could do grouping right now if I wanted to. Because look at the, see, I have the 1 and the negative 6. Now, do you see a GCF between the second pair What would happen if I divided both of these by 4 right now? I would get 1 and negative 6. See how they match? That tells me that I could do this by grouping. Alright, so if you're comfortable with grouping, it would be just as easy to do that right now. I'm just going to show it real quick. If I did grouping, so what I have here, putting the variables back in, I've got, what, x to the third power minus 6x squared plus 4x minus 24. So if I wanted to finish this problem by grouping, you know, I would take the first two and the second two. The GCF here would be x squared, and that's going to leave behind x minus 6. Over here the GCF is 4, and that's going to leave behind x minus 6. Okay, if I pull out the x minus 6, then that's going to leave behind x squared plus 4. Okay, so see this x minus 6? That's this that I already found. Okay, the x squared plus 4 is my new factor, which I need to write down. Now, and I could go from here and find the zeros by setting this equal to 0 and solving it. But I'm going to go back and do it the other way first. So I could do it by grouping like I just showed you. However, since we do have two zeros given, if we want to, we can use the other 0. So I'm going to go ahead and show that way now. So I could keep going. I have another 0 of 6, so I could just put the 6 right here. Please do not go back to the blue. Do not go back to the original problem. Once you have a 0, never go back. Okay, we started off with 1, 2, 3, 4, 5 numbers. Now we have 1, 2, 3, 4. Okay, you never want to go back to 5 again. Our goal is to get down to 3. Okay, so anyway, so I will keep going. Okay, so 1 times 6 is 6. That makes 0. 0 times 6 is 0. That's 4. 4 times 6 is 24. Alright, and of course that's another root. See how now we're down to 3? First of all, that's 6. You know, that gives us our factor of x minus 6. Now this is x squared plus 4. Okay, which of course we can go ahead and set this equal to 0 and solve. Alright, this x squared plus 4 is the same as what we have right here. Alright, so I could bring this down at this point if I didn't already find it by grouping. Anyway, to find the zeros that go with it though, I will solve it this way. So I'll have x squared equals negative 4. And then I will need to take the square root of both sides. Don't forget your plus or minus when you do that square root. Okay, ignoring the negative sign for a second, the square root of 4 is 2. So that would be plus or minus 2. Except for, you know, if there's a negative under a radical, that is I. Okay, so we have plus or minus 2i. So we will bring that down. And I like to write it separately as 2i and negative 2i. Okay, so really the direction said find all roots of the function. So this is really what we're supposed to find, these 4 roots. Writing it in factored form is kind of what we're used to, so I went ahead and showed it, but it's really extra according to the directions. Alright, anyway, moving on. Number 7. Write a polynomial function for the graph shown. Consider zeros and end behavior, and leave your answer in factored form. Okay, so we have to remember that sure, we have these zeros. Okay, so I have a 0 here at -2, which means I'm going to have a factor of x plus 2. Okay, I have another 0 here at 1, so that means I'm going to have a factor of x minus 1. And then I have another 0 here at 3, which means I'm going to have a factor of x minus 3. However, there are two other things I have to consider. Depending on how the graph behaves at each one of these zeros, I will know what the multiplicity of each one of these factors is. In other words, I should know whether it's a single factor or a double or a triple, you know, the degree, the exponent. And what we learned was, if the graph just passes straight through the 0, then that's a single root, a single factor. Alright? If the graph bounces off of a root, that means it's a double. So this root here at +3 means this factor of x minus 3 is a double. Okay, so it should be squared. Now, what's happening here at a root of 1 is called an inflection. An inflection is where, I'm just making it a little bit more clear, it's where you basically, it's like having half of a parabola and then the other half of the parabola going upside down. That's called an inflection. And I know it's hard to see because it's very shallow, but this is an inflection happening. It's bending in, and then it's curving out. You know, I'm exaggerating it to make it more obvious. But even though it's a shallow dip here, it's curving in, and then it's curving the other way on its way out. That is an inflection. And at an inflection, that lets you know that it is the third power. It's a triple root. Okay, so I'm going to have to cube that factor. Alright, so you have to take that multiplicity into account. But the other thing you have to watch out for is the leading coefficient. See how both arms of this graph are pointing downward? Just like if we were talking about a parabola, we'd be looking at a parabola with the same end behavior with both arms pointing downward. But this would clearly be the negative version of a parabola because it's upside down. Positive parabolas go up like that, okay, if it's a positive leading coefficient. Anyway, because this is upside down, both arms reaching down like an upside down parabola, that lets us know that this is a negative leading coefficient. So there's our function in factored form. Okay, and for number 8, we pretty much have to do the opposite of that. We're given the function, we need to sketch a graph. Okay, so because of this factor of x plus 4, we know we have a root at x equals -4. So there's a root there. This is going to be an inflection because it's a triple, so I know it's going to be one of those inflections. Alright, it's going to be doing like this type of a deal. Now, x minus 3 factor means I have a 0 at x equals 3. Because it's squared, I know that's going to be a bounce. Okay, so x equals 3, there's going to be a root right here. Now, I need to think about the end behavior and the degree. See how I have 3 of these and I have 2 of these. That means the degree of this thing is 5. 3 plus 2 is 5. So I'm looking at a degree 5. That's odd. Alright, odd functions, odd degree functions either behave like a right side up end behavior, that's when it's positive in leading coefficient, or it's going to behave end behavior like an upside down n. Okay, that's your negative leading coefficient. Well, see that minus sign in front? that tells me that this is the version that we should be looking at. Alright, it's negative, so it's going to behave, as far as the end behavior goes, it will have the end behavior of an upside down n. Okay, so I needed that because that tells me to start off up high. Okay, just like this starts off up high. So I'm going to start off up high, and then I'm going to do my inflection and my bounce. So starting off up high, and my inflection would be something like this. Okay, so there's my inflection. Now I need to come back around in time to do a bounce off of this. Okay, so not the prettiest graph I've ever drawn, but that is good enough. Okay, so it has the correct end behavior, like an upside down n, rises on the left, falls on the right. I have an inflection at -4, and I have a bounce at +3, so everything works out. Okay. Number 9. Alright. By the way, I want you to notice at no time during this process have I used my TI-30 XS multiview. You better assume that you are not going to be allowed to use the TI-30 XS multiview, which I know is very sad for us. But notice we haven't needed it. I've given you the information that you needed without it. So please make sure that you are not using your TI-30 because you need to be prepared to not use it on the test. Okay. Hold on, and let me get this over here. Yeah, show all work. What? Alright, anyway, so how do I do this without TI-30? Well, I'm going to use the graph, of course. Looking at the graph, I see we have zeros at -4, 2, I don't know what that is, but then there's 3. So I'm given 3 zeros. That's plenty of zeros to deal with. In fact, let's just start writing some of these down. Okay, so we have 1 at -4. Alright, we have a 0 at -4. Okay, that means we have a factor of x plus 4. We have a 0 at -2. Okay, which means we have a factor of x plus 2. And we have a 0 at 3, which means we have a factor of x minus 3. Alright, now this is degree 4, so there should be 4 zeros. So I'm only missing 1 0. Okay, so this should be pretty easy. Alright, no TI-30 needed. So let's do it. Okay, let's just, I'm just going to go in order. So using my -4, okay, I've got 3, 8, -33, -62, and 24. Okay, so that's going to be -12. So that's going to be -4. So that's +16. That is -17. That is going to be 68. Look, 4 times 17, you probably don't know that in your head. So even if you're not allowed to use your TI-30 XS multiview, you can still use a 4-function calculator. So don't worry if you need to multiply 4 times 17, and assuming you forgot how to do this, which I kind of hope you know how to do, but you can still use the 4 function, so no worries. Anyway, back to business. So this is going to be 6, and that is going to be negative 24. Okay, so we used the negative 4. So, but we can keep going. Let's use the negative 2 now. So here's my negative 2. Alright, I just put it right here, and I keep going. Okay. Alright, so that's going to be negative 6, negative 10, that'll be 20, that'll be 3, and that'll be negative 6. Boom. Okay, as soon as we have 3, we can either factor or use the quadratic formula. Okay, so putting these variables back in, this is going to become, I think I'm just going to squeeze them in right here. This is going to become 3 squared minus 10x plus 3. Okay, so I bet this will factor. Okay, 3x squared is going to be 3x times x. Now look, we have another 0 that we haven't used yet, this 3. That means, you know, as we saw here, that we're going to have a factor of x minus 3, which we haven't found yet. So guess what? I'm going to use that information. I know I have an x minus 3 coming, so boom, there it is, x minus 3. So, and you know what? I knew this had to be 3 times 1 anyway, and I knew the 3 wouldn't go here anyway, so I guess I didn't really have to do that. Anyway, to get a positive 3, I would need a negative times a negative to make positive 3. Also, inner, we have negative 1x. Outer, we have negative 9x. Together, that makes negative 10, so booyah. Okay, so the x minus 3, there it is. I was waiting for it. There it is. But this is the other one, 3x minus 1. That's the new one. Alright, that's the last one that I needed. And I could use that last one to go ahead and find my last 0. Now I can do this in my head and see that this last 0 is going to be 1/3. But just in case you can't, I'm going to show it. If I do 3x minus 1 equals 0 and solve, then that's what you do. Alright, so then I would have 3x equals 1, and then I would divide everything by 3. Okay, and that's how I'm coming up with x equals 1/3. That's where this is coming from. Alright, so there's my factored form, and here are all of my 4 zeros. And it makes sense. See that 1/3? You can see that this is approximately 1/3. Alright, it's 1/3 of the way over. So if I had gotten something that was not between 0 and 1, I would have known I made a mistake. Alright, let's move on. Number 10. Seems like same thing. Alright, so let's just dive in and do what we just did. Once again, I see I have zeros. Okay, I have a 0 at negative 2. Guess I should use a different color. I have a 0 at negative 2, and I have a 0 at 3. Okay, so 0 at negative 2, which means a factor of x plus 2. Alright, a 0 at 3, which means a factor of x minus 3. Alright, again, this is a 4th power, so I need 2 more roots and 2 more factors. Well, I guess I don't know how many more factors, but I definitely need 2 more zeros. Well, let's use the 2 that we've got and see what happens. I'm just going to go in order. So let's start with our negative 2. Okay, so I've got 1, negative 3, negative 1, 9, and negative 18. Alright, 1 times negative 2 is negative 2. That makes negative 5. Multiply, that makes 10. That makes 9. Multiply, that makes negative 18. That makes negative 9. Multiply, positive 18, 0. Okay, grouping would not work. That would make 1 and 1, which is not what I have here. Okay, so no grouping, which is fine because I have another 0 anyway. So I used the negative 2. Now I'm going to do the 3. Alright, just bring the 3 right down and pick up where you left off. Again, do not go back to the blue. Alright, don't go back to the 5. Stay with the 4. We're hoping for 3. Okay, so we'll go from here. Okay, 1 times 3 is 3. That's negative 2. Multiply, I get negative 6. That's 3. Multiply, I get 9. That, of course, is 0. Okay. Putting the variables back in here, I have x squared minus 2x plus 3. Alright, if this could factor, I would do it. Okay, x squared would be x times x. Alright, at first this is looking good because I'm thinking 3, that's 3 times 1, right? To make negative 2, I would need a negative 3 and a positive 1. What's wrong with this? It's not giving me positive 3. Alright, negative 3 times positive 1 is negative 3. But I had to have these signs this way to make the negative 2. So there's no way I can get the negative 2 and the positive 3 at the same time. So that means this is unfactorable, which means I need to either do the complete the square, or I need to use the quadratic formula. I'm going to go ahead and do the quadratic formula because it seems more popular among my kids. So quadratic formula. Just off to the side here, let me just remind you, the quadratic formula says x will equal the opposite of b plus or minus square root b squared minus 4ac all over 2a. That's what I'm doing. Okay, but I'm doing it in purple. Alright, so you know, I've got a is 1, b is negative 2, and c is 3 from these coefficients. So, opposite of b. So since I'm starting off with negative 2, opposite of b will be positive 2, plus or minus square root of some stuff, all over 2a. Well, 2 times 1 is just 2. Now, I always calculate this b squared minus 4ac by itself. So today will be no exception. Okay, so b squared minus 4ac. I think I'll do it over here, in fact. B squared minus 4ac. B squared, so that is, b is negative 2, so b squared is 4 minus 4ac. A is 1, so I really don't need to put it, so I'm going to go straight for the c, which is 3. Alright, so this is 4 minus 12, so this is negative 8. Alright, so we really didn't need a calculator for that. So that's where my negative 8 comes in. Okay, b squared minus 4ac. Okay, what about it? So I just need to reduce this and stuff. So this is going to make x equals 2 plus or minus. Okay, I know I'm going to have I because that negative under the radical. So let's talk about how do I do the square root of 8. Alright, I will just do this off to the side. Okay, look, check it out. The square root of 8. So normally I would use my TI-30 for this, you know, for your benefit. But just in case you can't use the calculator, just remember 8 is simply 4 times 2. So radical 8 is just radical 4 times radical 2. But the square root of 4 can be simplified. Square root of 4 is 2. This cannot be simplified, so you just bring it down. Okay, so the square root of 8 is just 2 radical 2. So that's why we'll have 2 radical 2. But don't forget the I. Because I had a negative under the radical, there will be an I and it goes in the middle. So 2I root 2. Alright. Now, let's not forget the denominator here. So all of this is divided by 2, all over 2. Let's bring that back. And now it's time to reduce using our heart, like we do. Okay, so I have my heart set on these 2's. You feel me? Alright, and the way the heart works is if all 3 of these numbers are divisible by something, we must do it. It has to be all 3. If this 2 right here were 3, I would be finished. But since all 3 of these are divisible by 2, I will divide by 2. And what I will get, I'm just going to have to squeeze it in right here. Let me go back to purple. What I will get is, I missed. What I will get is x equals, now 2 divided by 2, that's 1. So I have 1 plus or minus. 2 divided by 2 again is 1, but this time I don't have to put it because I have the rest of this. I have I radical 2. So this is the bottom line. Okay, once you reduce 1 plus or minus I radical 2. So let's go ahead and write these separately as 1 plus I radical 2 and 1 minus I radical 2. Okay, so that's it for the zeros. Okay, it was a 4th degree, so I was expecting 4 zeros, and there they are, 1, 2, 3, 4. However, factored form, we're not quite finished with the factored form. This is clearly not enough. This would only be degree 2, 1, 2, and it should be degree 4. So what's missing is this trinomial. Once we got x squared minus 2x plus 3, and we tried to factor it and we found it couldn't factor, then this unfactorable trinomial is itself the final factor. So it must be included among our factors. So here we go, x squared minus 2x plus 3. Okay, so this would be the factored form. Notice now we have our x to the 4th power because there's x, x, and then 2 more x's. That's a total of 4. So just a little way of checking. So that's it for number 10. Alright, what's up with number 11? Okay, number 11 is mentioning this possible rational zeros. Alright, if I ask you to list the possible rational zeros, I'm indirectly referring to the rational zero theorem. Okay? The rational zero theorem, alright, let me see if I can get a little bit more space on here for instructional purposes. Alright, the rational zero theorem tells us that the only possible rational zeros are going to come from the constant term and the leading coefficient. Alright, and I'm just going to use the positive versions of both of these. So it's like this. If I'm talking about numerators and denominators, okay, n over d. The possible numerators are going to come from the constant term, and the possible denominators are going to come from the leading coefficient. And when I say come from, I mean they're going to be factors of. So the only numerators will be factors of 5, things that divide into 5. Well, that's a very short list. Alright, it's just only 1 and 5 go into 5. Okay, same thing with the possible denominators. They have to be factors of this leading coefficient. The only factors of 3 are 1 and 3. Okay, those are the only numbers that divide evenly. Now, the way we can use that to get all of the possible rational zeros. Now, when I say rational, that means we're not counting imaginary zeros. We're not counting the ones that have radicals in them. Alright, it's just the ones that are like either integers or fractions. Anyway, I am going to mix and match these numerators and these denominators and see what kinds of different numbers I can come up with. It's best to use a system. So for example, I will first use these numerators all with a denominator of 1, and then I will use these numerators with a denominator of 3. Okay, so starting with these numerators, so I've got 1 and I've got 5. Those are my numerators. So I'm going to start with a denominator of 1. So that would make 1 over 1 and 5 over 1. So I've taken both of these and I've put them over 1. Okay, and then I start over. Okay, so I'm going to do these numerators again. So I'm going to go 1 and 5 again. But this time I'm going to put them over a denominator of 3. Okay, so 1 over 3 and 5 over 3. Okay, so I will reduce these and I will eliminate any repetition, and I will understand that all of these could be positive or negative. Okay, so it's really plus or minus all over the place. And this will give me all of my possible rational zeros. So let's see. So I've got, well, 1 over 1 is just 1. So I've got plus or minus 1. Alright, 5 over 1 is just 5. So plus or minus 5. And then 1/3. So plus or minus 1/3. And then 5/3. So plus or minus 5 over 3. So these are the possible rational zeros. Okay, but as we often do, we're supposed to take this polynomial and write it in factored form and find all the zeros. Okay, so basically, for the first time, in the past, we either had graphs where we could look and see exactly what the zeros were. That was the last couple problems. We had that, or we had this problem where we were given the zeros on the chart, on the table, and we could use those with confidence that they were going to work. Alright, now this is the first time that we aren't given a graph and we're not given a chart, and we're not supposed to use our TI-30 XS multiview. What we're supposed to do is to start using these possible zeros and plug them in one at a time until we find one that works. I want you to go in order. So I want you to do positive 1 and then negative 1 and then positive 5 and then negative 5. I don't want you to have to mess with the fractions, so I'm really hoping that one of these will work before we get to the fractions. Okay, so let's do that. Let's start with positive 1. Okay, so this may or may not work. Okay, so if it works, great. we'll finish the problem as usual. But if it doesn't work, we'll try again with -1. Okay, so my coefficients are 3, -11, -19, and -5. Okay, 3 times 1 is 3. That's -3. -3 times 1 is -3. That's like -22. That's -22. That's -27. So that was a fail. Okay, that did not work. So 1 didn't work, so let's try -1. Okay, so how about -1? Okay, 3 times -1 is -3. That is -14 times -1 is +14. That is -5 times -1 is +5, which does in fact make 0. So yay! Okay, we found one that worked. It only took 2 tries, so that was not very painful. So let's see. So this -1 that worked is then a 0. So let's go ahead and put that on the list. So we have a 0 of -1. Alright, which translates into a factor of x plus 1. Okay? To get the other two, because remember, this is a cubic, so there should be 3 zeros. So to get the other two, we will deal with this trinomial that's about to jump off. So what we have here, if I put the variables back in here, we have 3x squared minus 14x minus 5. So let's see if this will factor. Alright, because if it factors, that's always the easiest way. Okay, so 3x squared would only factor as 3x and x. 5 is like 1 times 5. Alright, if this doesn't work, I'll try switching places. Inside, I have 1x. Outside, I have 15x. This is looking promising. I need -14. So -15 and +1 would make -14. Well, there's my +1, and this would make -15 outer. But will it make -5? +1 times -5 is -5. Okay, so this is the correct factorization. So that's the rest. That gives me the rest of my factors. There's my 3x plus 1 and my x minus 5. Alright, that is the factored form, factored completely. Now the zeros from these are -1/3 and +5. So those are all my zeros, and there's my factored form, and there's my possibles. So I am done. I'm going to go ahead and just show one more time in case I lost anybody on where the -1/3 is coming from. I'm just going to show that real quick. Obviously, to get these zeros, we set these equal to 0. So we set 3x plus 1 equals 0. We set x minus 5 equal to 0. And we solve, you know. So subtracting the 1, we get 3x equals -1. Same thing, I added 5 to both sides. I get x equals 5. Okay, that's 5. Anyway, down here, I simply divide both sides by 3. Okay, so that's where I'm getting x equals -1/3 from. Okay, that's where these are coming from. Alright, that was number 11, once, for my Spanish speakers. Alright, we are nearing the end. Alright, write a polynomial function of least degree, leading coefficient of 1, and has these zeros. Alright, first thing you have to remember is that imaginary zeros always occur in plus minus pairs. So I see this 4i, so I automatically know that there is also a minus 4i that's included in the group. Alright, so just add it on because you know it's there. Now, to get a polynomial function going, what we really need is our factors. So, minus 5, that gives a 0 of minus 5 would come from a factor of x plus 5. Okay? A 0 of 0 would come from a factor of x plus 0. A 0 of 4i would come from a factor of x minus 4i. And a 0 of negative 4i would come from a factor of x plus 4i. Okay. The only thing I would change a little bit here is the x plus 0. Having plus 0 is silly. It's just x. It's just x. Okay. So, if I were you, I would multiply these together, and I would multiply these together, and then I would multiply the results all together. So, what am I talking about? It's a good question. You ask a lot of good questions over here. Dealing with this part over here first. It's really just the distributive property. So, x times x, that gives me x squared. Alright, x times 5, that's 5x. Okay, so that part is done. Now, multiplying these two together, let's see what we got. I feel like I should color coordinate this a little bit. Alright, yeah, okay, so if I do x times everything, alright, x times x, that's going to be x squared. Alright, x times 4i is positive 4i x. Okay. I'll use purple. So now I'm going to take the negative 4i and multiply that by everything. Negative 4i times x is negative 4i x. Negative 4i times positive 4i is negative 16i squared. I squared. I seem to be remembering something about I squared. But I'll come back to that. Meantime, 4ix minus 4ix, those are opposites, so they just cancel each other out. So I've got this x squared. I'm going to bring that on down. Now, this is going to become plus 16. Because what I just remembered about I squared was I squared equals negative 1. Okay, so this is really, what I really have is negative 16 times negative 1. And a negative times a negative is a positive. So that's why this is positive 16. Okay, so what I really have is x squared plus 5x times x squared plus 16. Okay, so once again I need to multiply all of this together, and that should give me my polynomial. So I like to color code this. So I'm going to multiply x squared by these two guys. So x squared times x squared is going to give me x to the 4th power. X squared times 16 is going to give me 16x squared. Now I'm going to do this times everything. 5x times x squared is going to give me 5x to the 3rd power. 5x times 16, 5 times 16, what's that? Alright. I went ahead and used my 4-function calculator, not my TI-30 XS Multiview, because I probably won't have that on the test. But it was 80, long story short. So 80x. I'm looking for any like terms to combine. I don't see any. So the only thing to do is to write this in standard form, descending exponent order. Okay, so it said function f. Okay, fine. So we will call this f of x, and we will put in order. So x to the 4th power, then comes plus 5x to the 3rd power, then comes plus 16x squared, and last comes plus 80x. Alright, descending exponent order. Alright, and that is how you do number 12. Okay, and the rest of this is a little review on factoring, which you will be responsible for. Okay, looking at number 13. The first step of factoring is to always look for the GCF. There is no common factor. But I notice that this is 4 terms, and I'm thinking grouping. Try grouping. So grouping says look at the first 2 terms and then look at the second 2 terms. Looking for the GCF, the greatest common factor of the first 2 terms, what I see is 15 goes into both of these. So here I go. So I'm going to have 15 and then n squared, not just n. Alright, the lower amount of variables here is n squared, so I need to pull out n squared. Okay, it has to be the most possible. So that's going to leave behind n minus 3. Okay, if you had any question about that, what I'm doing is I'm dividing by 15n squared. Okay, and these n squareds cancel out. 45 divided by 15 is 3. N to the 3rd divided by n squared is n. So that's what's really happening here. I think it will be helpful to you if you see this as a -1 sitting right there, because when you're doing grouping you really need a number to deal with. So I'm going to put that 1 out there and make my parentheses. If I divide everything by -1, sort of like I did just now with the 15n squared, then it's easy to see that this will be n minus 3. Or another way to think about it, distributive property. If I did -1 times n, -1n. If I did -1 times -3, that would give me the positive 3 that I started with. So looking good. Anyway, it's important that these parentheses are the same thing. If they are, then that makes them a GCF all over again that needs to be brought out front. Factored out, as it were. Notice we do not square it. Alright, you just bring out the GCF. You don't change the exponent on it. Once these are pulled away, that's going to leave behind the 15n squared and the -1. It's going to leave that behind. Okay, and in this particular case, that will be the end. Alright, 15n squared does not factor any further. Alright, because 15 is not a perfect square. Please understand that if say this had been n minus 3 times 16 n squared minus 1. Say this had been a 16 instead of 15. I would not have stopped here. I would have kept going. I would have done n minus 3. This is the difference of 2 squares. So I would have gone 4n plus 1 and 4n minus 1. And then this would have been my final answer. Okay, if it had been a 16. But that's not what happened. so that was just a big what if. So that is the final answer for number 13. Okay, number 14. First step of factoring is to look for a common factor. This time I do see a common factor. 3 goes into both, and I see the n squared here. So the GCF is 3n squared. So when you do the GCF, you just make one set of parentheses. Now, if I divide to see what's happening, okay, if you need this, this is what you do. Okay, if I divide like this, then you will notice that what's on the inside, the 3's cancel out, n to the 4th divided by n squared is n squared. 12 divided by 3 is 4, and the n squares cancel out. So I get this. Does this factor any further? No, it does not factor any further. All right. If this were a minus, I would have kept going. So you need to bring this down a little further. If this had been n squared minus 4, then I would have gone n plus 2, n minus 2. But when it's addition, it cannot be factored anymore. So that is the final answer for number 14. Alright, number 15. You have to recognize this as the sum of two cubes. Alright, now whether it's the sum or the difference of two cubes, it's really the same pattern. And the pattern is, it's always going to factor as a binomial and then a trinomial. A 2-piece and a 3-piece. The binomial comes from the cube root of each one of these things. Okay, the cube root of 125 is 5. Alright, because 5 to the 3rd power is 125. Alright, the cube root of n to the 3rd power is just n. Alright, it's addition. Bring it down. 8 comes from cubing 2. Alright, so finding the binomial should be kind of easy. Once you've got your binomial, really you can forget about the original problem. Everything else I can get from the binomial. Okay, if I take these and I square them, that's how I get the beginning and the end. So 5n squared, if I take 5n, like 5n times 5n, 5 squared is 25. N squared is n squared. Alright, so square this, you get your beginning. If I take this and I square it, I get 4. Alright, plus 4. That just leaves the middle. For the middle, I multiply these two together. But it should be the opposite sign. So this is a minus. I'm sorry, this is a plus, so I'm going to put a minus. 5n times 2 is 10n. Okay, so this came from doing 5n times 2, but the opposite sign. Okay, and that's it. That's how you do it. Okay, last one, number 16. This is the difference of two squares. Alright, as long as this is even, if this is n squared, n to the 4th power, n to the 6th power, n to the 8th power, of course this number has to be a perfect square, like 25 or 49 or 36. But this is the difference of two squares, so we will follow the pattern of the difference of two squares. We'll split this evenly, so n to the 4th power would be n squared times n squared. And so 16 is 4 times 4, so n squared plus 4 and n squared minus 4. Now a common mistake would be to stop right here. but that would be a bad idea because one of these can factor more. Not both, but one of them can factor more. The n squared plus 4 cannot factor any further, so we will just bring that down. N squared plus 4. Sum of two squares cannot be factored. This, on the other hand, can be factored more. So we will do n plus 2 times n minus 2. And this will be the final answer right here. Alright, and that brings us to the end of this review. Alright, please make sure that you can do every single problem on this review, and make sure you can do it by yourself without looking at your notes, without watching a video. You know what I mean? There will be a blank version of this available. If I were you, I'd print it out and do the whole thing over again from start to finish, making sure you can do it yourself. Okay, good luck. I will see you on the next video.